Hello guys, this is daily push-up challenge day number 19 while solving a Putnam problem, this time coming from the year 1962. So before we read the problem, let's insert in there 5 push-ups. 1, 2, 3, 4, 5. And like always, let's write down our progress. Okay, so the problem reads, evaluate in closed form the summation from k equals 1 to n of n choose k squared, and then note that n choose k, which is of course the binomial coefficient, is given by n multiplied by n minus 1 all the way up to n minus k plus 1 all over 1 times 2 all the way up to k. Okay, so the first thing that we can do here is let me rewrite the binomial coefficient right here, the given one. So you have n minus 1 all the way up to n minus k plus 1. Note that the denominator, you can write it as k factorial, right? 1 times 2 all the way up to k. So that's just k factorial. Let's introduce a term here, okay? A one term, so that we can extend the multiplication in the numerator all the way up to 1, okay? So we insert n, we multiply it by n minus k minus 1 all the way up to 1. And then we do the same with the denominator. You have n minus k minus 1 all the way up to 1. So note that the term that we introduced in the denominator, that is nothing but, okay, so let me write that here, that is nothing but n minus k factorial, correct? And you still have the k factorial right here. And then the extended multiplication in the numerator, okay, when you multiply this original numerator by the one that we introduced, that is just nothing but n factorial, because now the multiplication is running from n all the way up to 1. And in fact, this is like a more useful form of the binomial coefficient. Usually this form right here is it's more malleable when it undergoes calculation. Let's continue with the push-up. 6, 7, 8, 9, 10. Okay, let's write that down. So let's write the problem. We're evaluating the sum of k equals 1 to n of n choose k, which we write as n minus k factorial, and then n factorial in the numerator multiplied by k squared. What we can do here is, so sum k equals 1 to n of n minus k factorial multiplied by in the numerator n factorial. So your k squared, you can write it as, so this is like a pro move right here, you can write that as k times, let me see, k minus 1 plus k. Okay, so note that when you expand this term in the square bracket, k times k minus 1 plus k, that's just k squared, correct? But I wrote it in that form so that it can interact with the k factorial at the bottom. And when I say interact, I meant because k factorial, when you expand it, it becomes something like k times k minus 1. And you can see some of the terms, the k's in the numerator now will cancel the expanded k factorial in the denominator. Okay, so now what happens is so now we get here two terms. Summation of k equals 1 to the n of n minus k factorial, k factorial. In the numerator of the first term, you have n factorial k minus 1. Second term, you have summation from k equals 1 to n of n minus k factorial, k factorial. In the numerator, you have n factorial times k. Okay, so before we proceed, note that in the first term, okay, in the first term, k equals 1 is 0, correct? Because look, you have k minus 1 in your denominator, okay? So therefore, this summation starts at k equals 2, correct? Because k equals 1 is a 0 term. So you have in the denominator n minus k, and then in anticipation of the factors k and k minus 1 in the numerator, let me write k factorial as k times k minus 1 times k minus 2 factorial. So this is what I meant, that your k squared, when you write it as k minus 1 plus 1, plus k, it interacts with your k factorial. So you have n factorial k k minus 1. So these things, of course, will cancel with this one. In the second term, we have no problem because the k equals 1 term is not equal to 0. But again, in anticipation of the k term in the numerator, let's write k factorial as k times k minus 1 factorial. And then in the numerator, you have n factorial k. This term will cancel. Okay? So where were we? 10.
11, 12, 13, 14, 15.
And again, let's write that down. 15. Okay. So now, because we want a closed form, okay? So your final answer better not have any summation in it. So recall that the binomial theorem says that the summation of n choose k of x to the n minus k y to the k from from k equals 1 to n, or is it equals 0? It starts at 0. Yeah, it starts at 0 because the highest power is x to the n. Okay, so it should start at 0. Yeah, so this is equal to x plus y to the n. Okay, so now look, you have a very beautiful relation here when you let x equals y equals 1, because now what happens when you do that, you get something like summation of k equals 0 to n of the binomial coefficient n choose k, that's just equal to 2 to the n. Okay, so now we would like to use this identity in our summations here. But look, our summations, the first term starts at k equals 2. The second term starts at k equals 1. We want them to start at k equals 0 so that we can use this identity. Okay, so to do that, let's go back here. For the first term, let k minus 2 equals j. That way, so our index instead of k becomes j, and that way it starts at 0. So that's the sum of j equals 0. So now it goes all the way up to n minus 2. So you get in the denominator n minus, so k is just j plus 2. K minus 2 factorial is just, of course, j factorial. In the numerator, you get n factorial. In the second term, we let, because that starts at k equals 1, so we let k minus 1 equals j. So now the index starts from 0, but now it runs all the way up to n minus 1 instead of n. And so the denominator becomes n minus, so k is, of course, j plus 1 factorial. J factorial, that's just your k minus 1 factorial. In the numerator, you have n factorial. Okay? So note that in our identity, you have 2 to the n. The upper limit of your summation has to be n. Okay? But here our summation limit is n minus 2. So the upper limit of the summation should look like the upper argument of your binomial coefficient n choose k. So since our upper limit in the first term is n minus 2, let's write our numerator in terms of n minus 2. And you can do that because n factorial is just equal to n times n minus 1 times n minus 2 factorial. And then the denominator, I can always write that as n minus 2 minus j factorial. And of course, in the second term, you have summation from j equals 0 to n minus 1. So we want our numerator to have the form n minus 1. So we write n factorial as n times n minus 1 factorial. The denominator, you can write that as n minus 1 minus j factorial, j factorial. Okay? So now, n times n minus 1 in the first term, I can factor out of the summation. N I can factor out, and the reason is because I can now use this identity, okay, so that the form you will have like a closed form of the summation. Okay, so this becomes n minus 1. So you are left with n minus 2 factorial over n minus 2 minus j factorial. That is nothing but n minus 2 choose j, correct? And then the second term, I can factor out n, and then you have the sum of j equals 0 to n minus 1. So that is not the term that is left, n minus 1 factorial all over the quantity n minus 1 minus j factorial. J factorial, that is nothing but n minus 1 take j. Because note our definition here of our binomial coefficient, we're basically using this, okay, this definition. All right, so you have that. And then now we can use this identity. So because the upper limit is n of the sum and of the binomial coefficient, and then that's 2 to the n, therefore the upper limit here is n minus 2, the upper argument of the binomial coefficient is also n minus 2, therefore this whole thing is just 2 to the n minus 2. Same reasoning, this whole thing is just 2 to the n minus 1. Okay, and so all in all we now have something like n minus 1 multiplied by 2 to the n minus 2 plus n 2 to the n minus 1. Let me multiply this by 2 over 2, so that this whole thing will become n minus 1, 2 to the n minus 2, plus, so you have 2n, and then 2n minus 1, we divided that by 2, that becomes 2 to the n minus 2. So here you have plus 2n, they now have the same coefficient 2 to the n minus 2. Here you have minus n from the minus 1, and then you distribute n. Okay, so therefore all in all 2n minus n, you're left with the plus n. So this becomes n plus 1 2 to the n minus 2. Okay, so that is like the closed form of our evaluation right there. So we are now at 15, so we do this all the way up to 25.
16, 17, 18, 19, 20, 21, 22, 23, 24, 25.
Okay, and just to make sure we're not kidding ourselves with our final answer, let's try to evaluate this using Math Studio. Okay, so to see if this is indeed our final answer. So we're trying to evaluate this closed form. Okay, this one. So let me introduce a blank notebook right here. So we're evaluating the sum of the binomial of n choose k multiplied by k squared, and then we're evaluating that from we're evaluating k, the sum of k, from 1 to n. Okay, so let's press enter, and voila, n plus n times n plus 1 multiplied by 2 to the n minus 2 is exactly what we got here. So that's the same. Okay, and so this is like a mathematical software, so that should be right. So at least we have like a validation, a confirmation of the calculations that we did. So therefore the closed form of the summation of from k equals 1 to n of n choose k squared is just n times n plus 1 2 to the n minus 2. Okay, but yeah, that's it guys for our day 19 of our daily push-up challenge. 6 more days to go. I'll see you next time tomorrow for day 20. Thanks for watching, and bye-bye.